All right, we are going to determine if the series converges or diverges and give a reason for our answer. So what I'm going to do on this one is I'm going to compare 4 to the n. This is going to be a direct comparison. And the reason I'm going to do that, or the reason I'm comparing it to that, is very similar to the squeeze theorem. When these things converge, remember, recall it's because they get down to 0 quick enough that the individual terms that we're adding that kind of create a rectangle, like a Riemann sum, when we are visualizing it. And when they get down to 0 quick enough, this thing converges. Well, if this gets down to 0 quick enough, then anything below that obviously is going to get down to 0 quick enough. So the idea is it's very similar to the squeeze theorem from Calculus 1. If I can show this is always below this, and this converges, then this converges as well. And the way that you do it is very straightforward. You know that the sine function is always between -1 and +1. Well, that implies then, because that's true, if the sine function is always in there, then that means that sine squared is always less than or equal to just +1. Right? Because I'm squaring, the -1, negative times a negative is positive, so sine squared is always less than or equal to +1. Right? It's always above 0, but less than or equal to +1 is the important thing. Well, let me put it there. Right? And then if I divide both sides of this, or all sides of this inequality by 4 to the n, I still get 0 is less than or equal to sine squared n over 4 to the n is less than or equal to 1 over 4 to the n. And so this is true, right? This is now true. We've proven that this sequence of elements is always less than or equal to this sequence of elements, and this converges. Therefore, this will converge. Determine it converges by a direct comparison test to 1 over 4 to the n.